Section 3. Guess what we're doing right now, guys? We're proving. Who's excited? We are proving triangles similar, okay? So you are going to see some of your 3-letter, and actually there's a 2-letter theorem in today's, but it's not like doing full-blown proofs. I mean, we'll do a couple, but we don't do a ton. And honestly, not on like quizzes and tests either. They're pretty straightforward. So instead of proving triangles congruent, remember we did SSS, SAS, ASA, AAS, and HL were the 5 ways we proved triangles were congruent last semester. This time, we're going to prove triangles are similar. So we're going to prove their congruent angles and proportional sides, right? The way we do that, there's 3 theorems instead of the 5. So the first one is actually the one that I asked you on your test. Does the AAA theorem exist? And you told me no. It does in similarity. So it's actually just AA because the third angle theorem means we don't actually need the third angle. And then we do AA with the little tilde. Okay, that means AA similarity. So if we have AA similarity, yeah.
So the tilde. So with Miss Strong, we used to put like an equal sign, and then on top is it still mean congruent?
That's congruent. This is similar. This is just saying like proportional now instead of identical. Okay. Yeah. So the congruent symbol, this one, means everything about the 2 figures is the same. Now we're saying AA similarity. So now it's not, the angles will be the same, but the sides won't be the same anymore. Yeah, so don't use congruence for these. That won't work. Okay, this one says, if 2 angles of one triangle are congruent to 2 angles of another triangle, then the triangles are similar. Okay, what that means is this. I'm going to draw you a little picture here. It's going to be real teeny. Sorry, we'll zoom in a little. Let's say you have these 2 triangles, okay? If I tell you right now that this angle is congruent to this angle, and I tell you that this angle is congruent to that angle, right now I can say those 2 triangles are not congruent, but I know right now that they're similar. They're proportional, okay? So this would be how we see the AA similarity theorem is if I know 2 sets of angles are congruent, then the sides have to be proportional. Okay, so that's one way to prove triangles are similar. The second way that we're going to prove that triangles are similar is one that you already used for congruence. This is SAS similarity. Okay, and SAS similarity says if an angle of one triangle is congruent to an angle of another triangle, and the sides that blank those angles, let's see if you remember this word. The sides that include those angles. What does that mean? What is the included angle? The one in between the 2 sides we're talking about, yeah. The non-included angle would be the one that's not between the 2 sides that we're talking about. So the sides that include those angles are, God bless you, proportional. Then the triangles will be similar. Okay, so SAS similar to what we did before. If you have a triangle like this and a triangle like this, and I tell you these angles are congruent, but now I tell you, let's say this is 2 and this is 4, and this is 3 and this is 6, okay? The sides here are proportional. 2 over 4 equals 3 over 6. If the sides are proportional and the included angle is congruent, SAS similarity says those triangles must be similar. They are proportional all the way through, okay? So that's SAS similarity. And then the last one, any guesses? It's another one we've used before. ASA doesn't work with this. No. It's SSS is the last one. So if you have side, side, side similarity, That basically is saying if the corresponding sides, all three of them, of two triangles are proportional, okay, notice it's not congruent anymore, proportional, then the triangles will be similar, okay? So just like we said before, if I have a triangle here and I have another triangle here, and this is 2, 3, and 4, and this is 4, 6, and 8, okay? If every one of those ratios is the same, side, side, and side, then I know those triangles are similar, okay? So 2 over 4, 3 over 6, 4 over 8, they're all 1/2. They must be similar. Okay, those are the only three that work. Nothing else works. Don't use ASA, don't use AAS, don't use HL. None of those work with similarity. These three work with similarity, okay? So let's take a look. We're gonna determine for these three problems here, are they similar? And if so, how do we know? Okay, so take a look at A. Would you say that those two triangles are similar? Why? AA similarity, right? You have an angle that matches up with an angle and another angle that matches up with another angle. So that's AA similarity. So we can say, and now this is important, name it correctly. If I say triangle ABC is similar, not congruent, right? Don't put the equal signs, just the tilde. ABC is similar to what triangle? ABC would be YZX, right? Got to go in the same order. So double arc to single arc to no arc for our angles there. You can do them in any order. You just have to match them up. So ABC is similar to YZX by what theorem? By AA similarity. So this would be your answer. Are they similar? They are similar by AA. All right, look at the next one here. Letter B. You have two triangles. Now, right off the bat, you can rule out two of our theorems. Which two? Can't be AA because they told us nothing about angles. Can't be SAS because they told us nothing about an angle. It could be SSS, okay? But you still have to check it because if they're not proportional, it's not SSS. So let's check it. I typically say go in order. So the smallest side on the one triangle corresponds to what on the other one? The 10, the smallest side on this one. So 14 to 10 would have to equal, now do the next smallest, 21 to what? 15. To 15, yep. And then the third one would be 28 to 20. Okay, what do we have to do from here? Simplify, reduce those fractions, right? So 14 over 10, if we divide by 2, we get 7 over 5. 21 over 15, divide by 3, we get 7 over 5. And then the last one, 28 divided by 20, divide by 4, and that's 7 over 5. So because they all came out the same ratio, then we know they're similar. So now we name it. Careful how you name this. Triangle what? ABC is similar to, does it have to be ABC? No, you can pick any order you want. It just matters that the second one matches up. So ABC would be similar to what? EFD. Okay, by SSS. Okay, and now here's the deal. You have to, when you give SSS or SAS, anything that has sides, you give the scale factor as well. So with a scale factor of what? 7 to 5. Could I have said all of this with a scale factor of 5 to 7? No. But if you had named them the other way, if you had said triangle EFD similar to triangle ABC, then you have to say 5 to 7, right? So just pay attention. Order matters. Keep a good order there. Questions on that? Yeah.
Is it only SS that we use the scale
Anything that has an S in it. So SSS and SAS will need a scale factor. Yeah. Okay, letter C. This one's probably the trickiest. We're looking at triangles being similar. So you have this triangle. Right, here's one triangle. Do you see the other triangle? The big triangle, right? The whole thing. This triangle. So when you're working with triangles that overlap like this, it might behoove you, you don't have to, but it might be helpful to just redraw them so that you know what your total sides are. If you want to, great. If you're like, nope, don't need to, I can totally see it, then don't. But I'm gonna redraw it for anyone that needs to see it. So this would be A, B, E, and this is a length of 9 and 12. And then the other one is more like this. This is D, A, and C. What is AC? 17. Make sure you add those together. You want the whole side, not just 5, okay? And then AD is 12. Okay, question. Do you see anything about those two triangles that we know that's not marked for us? What? What do you see, William?
Angle A is congruent between them because it's the same angle.
Same angle. It's a reflexive property, right? So because this angle is the exact same angle in both, mark them congruent. Because now you should be seeing the potential for what? Which theorem? SAS, okay? Don't just assume SAS because they still have to be proportional for SAS to work. But there's a chance SAS works here. It's not going to be SSS. We don't know the third side. We don't know a second angle, so it's not going to be AA, but it could be SAS. So now check it. What would our ratios be? If we start with 9, 9 to 12 would have to equal 12 to 17. Are those equal? No, you can't reduce the 12 to 17, right? Not equal. So are they similar? We would say no, these are not similar. Okay, and if they're not similar, that's all you have to write. I want to see why they're not similar, but then just tell me not similar. Okay? Okay, then a proof. Okay, so this says, given that the two, oh, I didn't change it. Sorry, this should be AC is parallel to MP, my bad. Which means that's what it is here too, but that's okay. Given that the lines are parallel, prove that the triangles are similar. Good old proofs, right? Back to chapter 4 a little bit. So the first step is what? Every single time, the given. Free points. How do I know then, second step, how do I know A is congruent to P? And how do I know C is congruent to M? Alternate interior angles, AIA. Okay, because lines are parallel, alternate interiors have to be congruent. So step 3, how do I know the triangles are similar then? AA similarity. We have 2 angles that correspond to 2 angles. Now technically, there's actually 3 angles that correspond to 3 angles, right? Because you have vertical angles. You don't need that. You don't have to give that step because we have enough with the first 2. Okay? Okay. Last thing. Indirect measurement. Basically what you're doing here is you're measuring things that you can't measure with a ruler or a yardstick or a, what are those things called? Why can't I think of the name right now? That like a construction man would use. What does he measure? A tape measure, thank you. So that's not gonna cut it. It's like this huge building. I wanna know how tall is our gym, right? You have to do that indirectly because you can't just measure that big wall. I mean, you could. We're not going to. It would not be easy to. So instead, we measure indirectly. Let me show you how that might look. Example 3 here says, Ben places a mirror 40 feet from the base of an oak tree. You get to be artists again today. Twice in one day, you get to do drawings. What'd you guys draw for your present?
V-Bucks.
What?
Oh, like in chapel?
Yeah, in chapel. What'd you draw?
I drew Taylor Swift because I got Taylor Swift concert tickets.
Nice. That's a good one. Okay, so it says you have this oak tree 40 feet from the oak tree. So we're going to call this where the mirror sits 40 feet.
Oh, I need to do this.
Why is there a mirror?
I'm going to tell you. This is really cool. It's a good way to measure something. When he stands 5 feet from the mirror, so 5 feet away here, here's Ben. Okay. When he stands 5 feet from the mirror, he can see the top of the tree in the reflection. So when he looks into the mirror, his reflected view is that top point of the tree.
Is this like a thing in real life?
You could actually do this.
Can we do it?
It's fantastic.
We should do it.
We should do it, but I don't have a mirror. So, it says if Ben is 5 feet 8 inches tall,
Oh my gosh, Ben is tiny.
I mean, I feel like that's pretty average.
Oh.
What's the height of the oak tree? What do you see in this picture right now?
A man with a train.
What did we just create?
Art.
William.
2 triangles.
2 triangles. Hey, we know how to work with triangles, don't we? So you have a triangle here, and you have a triangle here, and maybe you have learned about reflection and refraction in science class, and you know that the angle of reflection will be the same with the ground that it comes in at and that it goes out at. Have you learned that in science class? Okay, well, I'm teaching you science then. It is true. This angle will be the same as that angle in a reflection, okay? So now we have to consider, how do I know that these 2 triangles are going to be similar so that I can measure the height of this tree without measuring the height of the tree? Well, Ben is standing straight up. The tree is standing straight up. That means those are both 90-degree angles, which means you now have what kind of similarity in that tree and that, yeah, AA similarity. So this is going to be AA similarity, which means your sides are all proportional, right? So in order to find the height of this tree, all you got to do is set up a proportion. Now there's one issue. Does anyone see the issue? There's inches. Inches are a little bit of an issue here, right? So you have options. You can convert everything to inches, or you can convert 5 feet 8 inches to just feet and use a fraction. Would you rather fraction or all inches? All inches. Okay. So 5 feet is 60 inches plus the 8 inches we have. So this is 68 inches. This is 60 inches. 12 times 40 is 480 inches. Did I do that right? I think so. So we can take this now and set up a proportion. So we're going to do 68 over what? What does the 68 correspond to? X, the height of the tree with the height of the man, equals what?
64.
Yes. Can you do 480 over 60? No. You have to go in the same order. Smaller to bigger equals smaller to bigger. So 60 over 480, and now you just cross multiply. What do we get? 68 times 480 is a very large number. Here's the only reason that inches maybe isn't the easiest. And then we divide by 60, and we get 544 inches. So that tree is 544 inches tall. If you want to convert that back to feet, what do? Divide by 12, and you get this, 45.3 repeating. So you could say it is 45 1/3 feet tall. If you really want to get fancy, you could convert that 1/3 of a foot into how many inches? 4. 4 inches. But you don't have to do that. Está bien?